Hello and good day to you. So today I'm doing a bit of a weave into genetic algorithms within Python. I'm trying to focus on decision trees and get my head fully around how to build decision trees and eventually possibly random forests. I like to try and learn the actual maths before just learning the code. Now, I've written this in Python standard library. I've got two main functions within a class for the decision tree. I didn't really need to make it a class, but I kind of wonder whether I'll make a class of random forests that manipulate and instance different decision trees. So it's probably useful for now. So what we've got here is to calculate entropy. It takes in a set of filters and a set of exclusionary filters, and goes down the reader of all the data, which it only keeps one instance around, which is a good lesson if you want to make a decision tree yourself, because you'll probably run out of memory with the amount of recursion involved in doing one. Now it goes down each row, checks each row to see whether it meets the criteria of the filters already specified, and then creates a collection of what the data is like for the forecasting value. So if I run this, you'll get that it's got 27% entropy as a base data, and it will reduce it down to 12, which is what it wants if it filters on the business travel, non-travel. You can see here the counts: nutrition no, nutrition yes, 414 and 36. So that's, if you were filtering on this in Excel, this would be your first point of call to get to a pure filter of the data. But then you see that it's moved along and considered if it's non-travel and department sales, I get a better value. And then it prints out, I found a leaf, I get 114 pure, zero entropy when I filtered on business travel, non-travel, and job role sales executive. So you can say that sales executives that don't have to travel are very happy people and they don't want to leave the company. You can see it then recurses back up to a earlier limb of the tree, and it starts with filter on business travel, non-travel. But instead of filtering on job sales executive, it looks at, well, I'm going to exclude job sales executive and investigate what I can find going down the other part. So then gone to department sales, looked at divorce, and it finds if I have business travel, non-travel, and it's a manager, but they're not a sales executive, that's 27 people, that's a pure node. Nobody wants to leave if they're manager and they don't have to travel and they're not a sales executive. Then it's recursing back up again. It's now taking the arguments that we're not looking at sales executives and not looking at job role manager, and but it's still filtering on where they didn't have to travel. You'll see it will go down, and it will find, well, if they're not a manager and they're not a sales executive, but they still don't have to travel, but they're educated in marketing, those people also want to stay. And so that's another rule we've got. And if we're going on, so technical degree, non-travel, not a sales executive, not a manager, not in marketing, 27 of those people didn't choose to leave this year. And if you can see, it just keeps on creating more rules to explain the underlying data and sort of filter it out into pure nodes if it can. Now, sometimes it can't create a pure node and it just sort of will stop. But it's one way of data mining to find rules within the set of data you've been given. And I find this really useful and really interesting because as a data person, I think if you've never experienced somebody in the business turning around and saying, well, I want you to do this, and either they're not going to explain the filters they want you to use, or they don't know the filters they want you to use, or the filters are in constant change. This is a lifesaver, because this is the ability to turn the tables and get an algorithmic method of reverse engineering the filters and the business logic being used there. Now, you probably will be thinking at this moment, well, it's not very useful if there isn't any right answer. And that's true, because all of this has pre-proposed so far that there are clean, nice end nodes where we can get a leaf that we can sort of create these filter rules from. And you can get an argument that sometimes you are going to have to remove certain leaves and certain rules, like this attrition number 1, which they tend to call as pruning. But as you can see, it just keeps on generating new rules. Interestingly, there's no rules it particularly finds which explain people wanting to leave this company that is, oh well, there is. So if you're none of these and you're divorced and you don't want to travel, you want to leave the company, and all 3 of them do want to leave the company. But if you eventually it will run out of same with that. So it doesn't look like if they were working for human resources and they're not married, they're not divorced. Sorry, it's just funny. But as you can see, it'll just carry on. It'll carry on creating rules until it's run out of possible zigzags and filters. And the way to deal with, well, as you see here, it gets to the end. It's run out of possible rules. So one solution to the fact that it's not very good at data where there isn't any final logical conclusions is that the way you use it is to set up a set of random forests where you create multiple decision trees from multiple different instances of the data or multiple starting points within the data, and it was based on different filters, and then at the end the random forest votes based on how many rules match what you're trying to define, and you take the largest amount of rules as the probable answer you're going to give this, and that has the benefit of being quite similar to at least one theory I know of how the human brain works, because one theory that they throw about is the human brain is basically a massive database of procedures and processes, and what our brain does is it chunks input coming in and finds the closest match of the process or procedure that it has stored in its brain to the current situation, and then takes that action based on some sort of heuristic. Now, in this instance, the heuristic being used is entropy. You can then, by having lots of these entropy trees developed, you can group them up as that big database of possible rule sets and apply the rule set that seems to fit best, and be in a constant state of pruning down to the worst rule sets. So I'll just quickly show you the code and then I'll be done. So mainly for me, I put it in a class, but that's mainly because at some point I'm going to probably build it up into a random forest. There's really 2 main functions. There is a function called learn rules, which does the testing of multiple different filters, works out the one with the best, with the lowest entropy, and then recurses back on itself twice. Once to take the do the situation where it assumes that it takes the argument of including the path that it went down, and then it also takes down the path that it didn't go down. And then, having done this recursion multiple times, it will probably only have a couple of instances of itself running at one time, so hopefully your computer doesn't run out of memory. If you do write one of these, do think about memory a lot, because of any recursive algorithm. If you get a mistake where it just keeps on calling back to itself, eventually, Python, it won't let you recurse anymore. But there you go. And my personal design is I added in try and accept to deal with that and print out where it got to an end, because my first attempt, it was actually a bug. It wasn't working properly, but my first attempt at making a decision tree, it just went on for ages, and then eventually said I'm out of memory. So, lesson learned. Anyway, I hope that's interesting. I might be tooting my own horn a little bit of, having to look, but I just wanted to learn this, and this seemed a good way to do it. So thanks, have a good night, bye.